called problem of motion. Problem of motion is a relationship between location or position of an object and time. T I'm using to represent time. R, a generic symbol for position. But today, for this lesson, focus on vertical position. Vertical position. So we're interested in knowing how the vertical position changes with time. The symbol I want to use for vertical position is going to be Z of t. Z of t is going to be my vertical position. So what does a vertical position means? I'll be measuring it in meters, and meters, so many meters above my reference level, so many meters minus so many meters below my reference level. What would be a reference level? Could be the top of this bench. That's my reference level 0. Above this and below this would be plus and minus z. Could be the floor of this room. That's z equal to 0. That's a very good place to choose a 0. So z, the vertical position, can take positive values, negative values. Our unit would be meters. So where is the object initially? Z of t at t equal to t initial. So I might sometimes even call this zi for z initial. Sometimes I might call it z0 for time t initial equal to 0. So the kind of questions that one is interested in, what is z final, or what is the position z at time t given the position at some initial time? How I'm going to answer that question? By saying z of t, z final is initial plus a quantity called delta z. So the whole problem of finding delta z final becomes finding delta z, because this we already know. So this splitting, that my problem of finding final position is nothing but adding delta z to my initial position, is a very successful strategy, and it depends on what is called reductionism. So in physics problem, I can say my final goal I can reach in this case a vertical position just by knowing where the object started and how many meters it moved. So t is only a function of t. So delta z doesn't depend on anything else. It doesn't depend on where I started from. Okay, it only depends on how long has the object moved. So the fact that delta z doesn't depend on where I start, doesn't depend on what time I start and things like that, has a fancy name. It's called space and time translation invariance. Invariance. Space-time translation invariance. This also relates to what is called space-time homogeneity. That means space and time today at 10:30, time and nature is going to behave same way as it did yesterday or tomorrow, or what it will do. So it doesn't depend. It means how much delta z is going to be. It doesn't depend on where I'm talking about, when am I talking about. It only depends on how much the time has lapsed. So this is a very, very strong and important requirement. That the quantity is the physical quantity we are talking about, and the quantity here is delta z. How far the object moves in the vertical direction depends only on how long the motion has taken place. So delta z, I will say delta z then, as I say, function of delta t, but really function of t initial minus t final minus t initial. So delta z depends on delta t, how long time has lapsed. So I can ask the question, what's the rate of change in motion? That brings me to velocity, constant velocity. Constant velocity is delta z. So since it's z direction, I'm going to put this symbol z. Delta z over delta t. This in meter, this in second. So velocity would be meter per second. What does it measure? Velocity measures how much object has moved in the z direction in how much time, how many meters, how many seconds. From the rate of change in z, one can also ask rate of change in v. That brings me to acceleration, which says find change in z, divide that by change in time. That would be acceleration in z direction, and that's measured in meter per second squared. So meter per second, divide one more time by second, so that gives you meter per second squared. So bottom line here, we got three things to worry about.